It is the 23rd of August, 9:25 a.m. Continuing on the preliminaries from Dummett and Foote, this time on the properties of integers. The integers z are among the oldest mathematical objects. Their properties have been studied since antiquity. Ancient number theory with the Greeks, especially Euclid, around 300 BC, formalized results on divisibility, greatest common divisors, and primes in Elements Book 7. The Euclidean algorithm, known to Euclid and perhaps earlier in Mesopotamia, this algorithm for finding the GCD, greatest common divisor, of two integers remains fundamental today. Euclid proved there are infinitely many primes. The idea that every integer factors uniquely into primes is implicit in ancient work and formalized in the fundamental theorem of arithmetic, Euler's totient function, introduced by Leonhard Euler in the 18th century to generalize Fermat's little theorem and study multiplicative structure modulo n, is also a thing worth noting. Now, the basic properties of the integers underpin much of algebra and number theory. We state them precisely and prove them in the modern set theoretic language. So let's check the camera real quick. Looks good. Attack. And let's start off with the well ordering of the positive integers. So this is known as the well ordering principle. And it states that every non-empty subset of the positive integers has a smallest element, m, such that m is less than or equal to a for all element a within the set A. So, for a basic proof of this, suppose A is non-empty. Let S equal 1, 2, 3, onward, intersect with the set A. If 1 is within the set A, we're done. However, check 2, 3, so on. in order. Because A is a subset of the positive integers, and these are well ordered, by less than or equal to, we eventually, of course this proof is not the most precise of things, but it's a rough proof. Find the first element of this minimal element M is the one desired. Could just do proof by induction, which is essentially what this is saying. It's just not as precise because I don't really need it to be right now. Now let's go. So let's look at a calculative example of that. Which is basically just a thing in practice. So let A equal the set n within the positive integers such that n is a multiple of 5 and n is greater than 12. This would essentially be equal to 15, 20, 25, so on. Suppose we then we have that m minimum of the set A is equal to 15. Now this concretely illustrates that a non-empty subset of the positive integers has a least element, and that's essentially what this is. Obvious, but intuitively, but you know, formalistically speaking, it's a bit of a more difficult case. Nothing too bad though. Okay. On to the next one, divisibility. For AB within the integers with A not equal to 0, we say A divides B if there exists C within the integers with B equal to AC. Lemma. if A divides B and A divides C, then A divides SB plus TC for all ST within the integers. Proof of this, write B is equal to AK and C is equal to AL. Then SB plus TC is equal to S times AK plus T times AL, which is equal to A times SK plus TL. And this shows that A divides SB plus TC. Now, calculative for this. Since 4 divides 20 and 4 divides 28, for any ST elements within the integers, we have 4 divides S times 20 plus T times 28. Take S equal to 3, T is equal to -2. And what we have is 3 times 20 plus -2 times 28 is equal to 60 minus 56, which is equal to 4. And indeed, A, which is equal to, A, which is equal to 4, does indeed divide 4. This is a valuable thing in a cryptographic sense. Well, I mean, all of this kind of is. I mean, it's essentially as if you get rid of it, you don't exactly have it now, do you? Okay. Now, on to the next property. Greatest common divisor. And least common multiple. The greatest common divisor of elements A, B within the the integers, with the exclusion of 0, is the unique positive integer d such that d divides a and d divides b, hence the common divisor part. And if e divides a and e divides b, then e divides d greatest. So write d is equal to a b, a coordinate, ordered pair, if a b is equal to 1, then we say a and b are relatively prime. Now here's a proposition known as Bezout's identity. For a, b within integers, with the exclusion of 0, there exists x, y within the integers such that the ordered pair AB is equal to AX plus BY, which we're just going to use this ordered pair to denote the greatest common divisor of A and B. So, proof of this. Well, there's this notion of the Euclidean algorithm, which we kind of discussed briefly in the historical part of this for context sake, but which I'll get into a bit more in depth later. But for now, suffice to say, encapsulate this, store it away in a black box to be used at some later time, but apply the Euclidean algorithm to A and B. This produces remainders R sub k satisfying R sub k minus 1 is equal to Q sub k R sub k minus 1 plus R sub k, with 0 being less than or equal to R sub k, which itself is less than the absolute value of R k minus 1. Now, when r sub n is not equal to 0, and r sub n plus 1 is equal to 0, what we have is r sub n is equal to the GCD of A and B. And we can do this thing, which we'll go more in depth into later, in which we substitute back substitute each r sub k in terms of A and B to express r sub n as a integer linear combination of A and B, which is what we set out to prove in fancier wording, but there it is. Yeah, and we'll see the division algorithm sort of generates a calculative example of this in play. So whenever we get to it. So the least common multiple. The least common multiple, L, of A and B is the unique positive integer such that, for one thing, A divides L and B divides L. For another, if A divides M and B divides M, then L divides M. You have that notion of the common divisor, and this time least. So we write L is equal to the LCM, least common divisor, of AB. Now, there's an interesting relation here, which is that the GCD of AB times the LCM of AB gives us the absolute value of the product of A and B. So, of course, you know, it's pretty cool. It's the simple things that count in life. Now, on to the aforementioned division algorithm. Euclidean algorithm. So, given A, B are elements of the set of integers with b not equal to 0, there exists unique QR within the integers such that A is equal to QB plus R, 0 with 0 being less than or equal to R, which is less than the absolute value of B. Now, the proof of this, proof of the logical consistency of this, roughly speaking, we have existence divide A and by B. In the usual sense, to get a quotient Q and remainder R satisfying bounds. Uniqueness if A is equal to QB plus R, which is equal to Q prime B plus R prime, with 0 less than or equal to R, R prime being less than the absolute value of B, then subtracting gives Q minus Q prime times B, which is equal to R prime minus R. The right side has absolute value less than the absolute value of B, so it must be 0. Ergo, Q is equal to Q prime and R is equal to R prime. Uniqueness. Existence and uniqueness. Now let's see a calculative example of the division algorithm in practice. So let's let A equal 101 and B equal 7. We seek QR with 101 equal to Q times 7 plus R, with 0 being less than or equal to R, which is less than 7. Now, dividing 7 times 14 equals 98. So, Q is equal to 14, and R is equal to 3. It's the closest one you can get to that. So 101 is equal to 14 times 7 plus 3. Matching the abstract definition. QR, with QR being in the integers, and 0 being less than or equal to R, which is less than the absolute value of 7. Simple enough. Let's move on to the Euclidean algorithm now. Euclidean algorithm. Repeated, it's basically repeated application, repeated application, I'd say that's, of the, because it's got more than just that. It's got more than just that, but I'll show that. Whenever I was making these notes, it was like, okay. Repeated application to the division algorithm to GCD of A and B, terminating with 0. And last non-zero remainder equal to GCD of A and B. Now, the proof for logical consistency that this actually is a thing that follows rules and that are to what we have found before and are valid roughly goes apply the division algorithm. A is equal to Q sub 0. B times B plus R sub 0. Well, I'll just say not, because if I just keep saying sub 0, I keep thinking about the Mortal Kombat character. Then B is equal to Q sub 1 R naught plus R sub 1, etc. Keep it going iteratively. Iterations. So, remainders strictly decrease in absolute value. And are non-negative. So, the process stops. It does have a terminating point. Now, what about the manner in which it does terminate? What about what it gives us, right? The last non-zero remainder divides previous two terms. This is kind of an induction proof that we're flattening down into, well, flattening down, rudimentarily verbalizing, yeah, I guess so. Divides the previous two terms in the sequence and thus divides any common divisor. So, it equals GCD of AB by definition. Let's look at a calculative of the Euclidean algorithm. So let's let A equal 252, 252, and B equal 165. Well, 252 is equal to 1 times 165 plus 87. It's a lot easier to do once you have the notes. already in hand. It's a practice thing. Like I was doing this for a cryptography class, and it's a bit of a difficult thing to learn to do. But 165 is equal to 1 times 87 plus 78. 87 is equal to 1 times 78 plus 9, and this is very valuable because it's just the cryptographic applications of this stuff is just enormous. 8 times 9 plus 6. 9 is equal to 1 times 6 plus 3. 6 is equal to 2 times 3 plus 0. The last non-zero remainder is 3. So GCD of 252 times and 165 is equal to 3. There is the last non-zero remainder. Now, there's this thing which I referred to earlier, which is back substitution. These help you get the zoo coefficients, because remember, we went over that. It was defined by what did we specifically call it though? Just don't want to mix up terms too much if I can help it. Bezout's identity. Yes. Not property. Okay. Bezout coefficients via back substitution. And that's going to be this, well, I'll just show you. 3 is equal to 9 minus 1 times 6. 6 is equal to 78 minus 8 times 9. And this implies 3 is equal to 9 minus 1 times 78 minus 8 times 9, which is equal to 9 times 9 minus 1 times 78. And from this, we have 9 is equal to 87 minus 1 times 78, which implies that 3 is equal to 87 minus 78 times 9 minus 1 times 78, and we'll just keep doing this. And what we eventually find is that if we do this iterative process of back substitution, what we get is that 3 is equal to 252 times x plus 165 times y. Clever. Very clever. And you'd solve and get these. And those would that's part of a cryptographic scheme. What was it? I think might be RSA. I think it's RSA, where you go back and you have to find primes. I think so, yeah. Okay, don't quote me on that, but you know. All right. Now let's look at the another calculative. For A is equal to 84, B is equal to 60, 84 is equal to 1 times 60 plus 24, 60 is equal to 2 times 24 plus 12, 24 is equal to 2 times 12 plus 0. Well, GCD of 84 and 60 is equal to 12. The LCM is a bit easier. It's LCM of 84 and 60 is equal to 84 times 60 over 12. Well, you have to get the GCD first, though. So, which is equal to 420. Which is blazing, man. 420. But with back substitution, what you end up getting here is 12 is equal to 60 minus 2 times 24, which is equal to 60 minus 2 times 84 minus 60, which is equal to 3 times 60 minus 2 times 84. So you can see, these this reoccurring pattern where a thing is divided into two such objects here, products, like we were dealing with before, to speak of the Bezout coefficients. But suffice to say, 12 is equal to negative 2 times 84 plus 3 times 60. Rearrange that. That's what you get. All right. Now, let's move on to another major thing when we talk about integers. Primes, which we've discussed because they're just so prevalent before, and fundamental, which we also talked about, theorem of arithmetic. Now, start with a definition. A prime well, they're one of the great leaders of the Autobots, but in this case, a prime is a positive integer. Is a positive integer p greater than 1 whose only positive divisors are 1 and p. Non-primes greater than 1 are composite. So let's look at a lemma here. lemma, which talks about the prime divides a product. If P is prime and P divides AB, then P divides A or P divides B. Proof. If P doesn't divide A, then GCD of P and A is equal to 1. Fair enough. Bazou's identity, because he's French, Bazou's identity gives Px plus Ay equal to 1 for some xy. Multiply by b. And what does this get you? Well, this gets you this gets you pbx plus aby, which is equal to b. Now, since p divides pbx and p divides aby, what we get is that p must divide b. So it must divide the sum. Fair enough. Now, calculative. Let P equal 5, A equal 14, B equal 15. Then what we have is AB is equal to 210, and 5 divides 210. 5 divides 210. Since 5 doesn't divide 14, right? Since 5 doesn't divide 14, the remainders 14, so it's 1 modulo 5. It must be the case that 5 divides 15. Well, remainder is 14 equal to -1 mod 5. I don't think we discussed modular arithmetic though, but just hold that. It must be that 5 divides, it's not another 1, let's fix that, divides 15, which holds. Now let's look at something truly fundamental, so fundamental that it has it in the name, which is the fundamental theorem of arithmetic. every integer n greater than 1 can be written uniquely up to order as n is equal to p sub 1 to the power of alpha sub 1, p sub 2 to the power of alpha sub 2, onward and upward all the way to p sub k to the power of alpha sub k. These multiplied with each other with distinct primes, p sub I, and positive integers, alpha sub I, Now, let's look at a basic proof of this. First off, existence. Induct, because this is a process, yes, on n if n is prime, done, no further work required, right? If it's prime, it's prime. If composite, if n is composite, also done, no proof needed, no. But if n is composite, yes, right? N is equal to AB, with AB being less than n. Then whoops, yes, with AB less than n, then AB is less than n, factor each by induction, and combine. Uniqueness. Suppose n is equal to p sub 1 to the power of alpha sub 1 all the way to p sub k to the power of alpha sub k, which is equal to q sub 1 to beta to the power of beta sub 1 times all the way, and these are products all the way up to q sub m, all the way up to beta sub m. With primes in ascending order, which is what I was getting at, but why not write it for now? So what we end up seeing here is that, well, p sub 1 divides q sub 1 to the beta 1 multiplied with each iteration all the way to q sub 1 to the power of beta sub, q sub m to the power of beta sub m. And so P sub 1 is equal to Q sub j for some j. And what we have from that is that we can actually cancel and repeat inductively this process to match all primes and exponents such that P must equal Q. Each P is equal to, primes and exponents. There's only one single prime, Primes and exponents. Not too much. Let's look at a calculative for this. 360 is equal to 2 to the power 3, 3 to the power 2 times 5. Yeah. 2,310 is equal to 2 times 3 times 5 times 7 times 11. I checked it before, but it's just like, well, why not check again? It's kind of fun. Okay, so each factorization is unique up to the order of prime factors. Euler's totient function. We're going to look at this thing here, which is Euler's totient function. Definition for n within, gotta hurry with this, for n within the positive integers, totient function of n is number of integers within, come on, write faster. Number of integers, 1 less than less than or equal to a, less than or equal to n, with the greatest common divisor a of a and n equal to 1. Now, there's this theorem, which, it originates in China. Chinese remainder theorem. Two moduli. I mean, so does, like, no, I'm not going to go into a history thing for now. Let mn within the positive integers. Let mn be within the positive integers, with the GCD of those being equal to 1. Well, what can you say about that? Well, for any integers a, b, there exists an integer x such that x is equal to a modulo m, a mod m, and x is equal to b mod m. B mod n. Moreover, this x is unique modulo mn. Okay. Still have some things to cover, but we're running out of time, so I don't know if I can actually make it. Let's see. If I can't, then I'll just save it for next lecture. Do I have time for that one? Okay. Proof of this since the GCD of m and n is equal to 1, we can say that Bezout's identity gives what? Well, it gives integers u v with um plus vn equal to 1. Now, define x equal to a times vn plus b times Then, modulo m such that x is equal to a times vn plus b times roughly, well, yes, no, yeah, right, okay, equal to a times 0 plus b times mod m. But is equal to 0 modulo mod m. And Vn is equal to 1 mod m. since Vn is equal to 1 minus um. So what we actually get then, x is equal to a times 1 plus b times 0, which is equal to a mod m. Okay, let's do this. Continue here. Yes. So, similarly, mod n such that x is equal to a times Vn plus b times um, which is equal to a times 0 plus b times 1, which is equal to b mod n. So, this satisfies both congruencies. Congruencies. I'm going to say congruencies. That just sounds better. If x prime is another integer, if x prime is another such integer, right? Let me erase this. It's too much. I'll go this way. Keep erasing. So if x prime is another such such integer, then m divides x minus x prime, and n divides x minus x prime. Now, as the GCD of mn is equal to 1, it follows that mn divides x minus x prime. So, x is equal to x prime modulo mn. Whew. It's unique. Up to modulo, yeah, sorry. Okay. We're going to look at one last calculative. One last calculative, and I think... Okay, yeah, we'll look at one last calculative. Sad. Okay, and then we'll call it a day. This is for the Chinese remainder theorem, solving a pair of congruences. So, say we're asked to solve x is equal to 3 mod 4, x is equal to 2 mod 5. Now, as to find each of those. So, what we do here is, well, we'd say since 4 times negative 1 plus 5 times 1 is equal to 1, we take u equal to negative 1, and v equal to 1, m equal to 4, n equal to 5, a equal to 3, b equal to 2, and set x equal to a times vn plus b times um to get 3 times 5 plus 22 times negative 4, which goes to equal 15 minus 8, which is equal to 7. Yes. So we broke this thing up into these variables, in case you couldn't, see that yet. But yes, we get 7. Now let's check this. 7, 3 mod 4, and, which is true, 7, 2 mod 5. General solution to this x is roughly equal. I keep on seeing this and I keep on saying roughly equal, but that's not true. X is, it's the 3 lines that are just messing with my head for whatever reason right now. But x is equal to 7 mod 20. And there we go. That's it for today.